Great, very good. OK, I have a tall order to be the last speaker, but I appreciate everyone for sticking around, and hopefully I'll be entertaining. This is a little bit different than what you heard before, but it's actually quite related to what Josh was mentioning. So I hope to tell you about how we can reduce simulation dependence with deep learning. So first, I should say that physics simulations are amazing. And even though the rest of the talk I'm going to spend telling you about how we should reduce our dependence on them, they're really great. They're very complicated. This is a schematic simulation of a simulation at the Large Hadron Collider. We simulate 20 orders of magnitude, and it's really amazing. But the deep physics sometimes can be debilitating for understanding nature. So let's try to see if we can do some deep learning without them. OK. So I'm going to tell you about some applications of doing deep learning with less simulation dependence in sort of totally different areas. So I'll first start with classification, then I'll give an example from regression, and then I'll end with an example from using generative models. So yeah, start with classification. So what's the problem? What is one problem? So one problem with classification in many areas of physics, in particular particle physics, is that we can't, even if we had infinite money, we couldn't pay physicists to label cats and dogs. Because thanks to quantum mechanics, it's not always possible. It's not even possible to ask the question, is this a cat or a dog? Or whatever the quantum mechanic analog of cats and dogs are. And so usually, the best case scenario we can hope for is having two mixed bags. And in the mixed bags, we have superposition of two different classes. So say we have the red class and the green class. We have two mixed samples that have some composition of red and green. And I don't get to observe the color of the circles, just I have two mixed bags. OK. And so the usual procedure is, let's say you have some simulation, where in simulation you can play God. So you can say pure samples. I have pure green, pure red. I train a classifier to distinguish them. So this is fully supervised learning. Then I can do some kind of calibration procedure. We heard about calibration earlier, which is where we spend most of our time calibrating everything. But then let's say we've calibrated. So calibration means make the procedure unbiased. And then I can apply to some new data set, and we're all happy. The challenge is that if the statistics of my training data set are slightly different than the ones in data, then of course I can calibrate to make my procedure unbiased. However, it may be suboptimal. And that's the thing I really want to talk about now. OK, so just this is the setup. And the idea is we want to be optimally learning directly from data. And in this case, data for us means unlabeled. So the data either have we know something about the data, but they don't have per instance labels. So as a reminder, this is the case we have. And the only assumption I'm going to assume, which is an important one, which is that the statistics of, say, the red are the same in the two classes. So the only thing that differentiates the left and the right bags are that they have a different fraction of red and green. OK. And so actually, you know many ways of learning in this case. So let's say, for instance, I assume something. So let's say I know the fractions. So I know the fraction of red and green, so F and G. So I can say that these two mixed samples are a superposition of pure samples. And if I knew the two fractions, it's a system of equations. I have two equations, two unknowns. I can solve. And this works really well if my feature space is like 1 or 2 dimensional. But imagine my feature space is like 1,000 dimensional, or even higher. Then this doesn't work very well. It's pretty intractable. But you can still do learning. So one way of doing this is to basically learn with label proportion. So this is the usual machine learning paradigm. You have a loss function. You learn a function f prime, and you have per instance labels. So you minimize this loss. What you can do instead is, suppose I don't know the per instance labels. I don't know the TIs, but suppose I know the fractions. So you could say, OK, I know the fractions y. So I'm going to just basically move this sum inside the loss function. I'm going to learn on average. So then I could say, I want my per instance classifier to predict such that on batches, I get the right proportion. And this is a pretty straightforward generalization of the solve the system of equations thing. So this is great. But it still has the problem that I have to know y. It turns out that there's actually some tolerance. There's a neighborhood around y where you can kind of be wrong and still get the same classifier. But nonetheless, wouldn't it be great if I didn't have to know y? And it turns out the answer is yes, you don't have to know y. And I don't have to write down any equations. Basically, what you can do is very simple. It's actually almost exactly the same idea as was described earlier with the noise to noise, as you were mentioning, which is basically I can make labels. Call everything in this one 0, everything in this one 1, every instance. And now everyone has a label. And I just train a classifier to distinguish the two mixed samples from each other. And once I've done that, I take the resulting classifier to distinguish red and green. And it turns out that you can actually prove pretty simply that this is optimal for distinguishing red and green, and the asymptotics that your classifier is sufficiently good. And I'll just show that. But OK, both of these approaches I just mentioned, so knowing the fractions or knowing nothing, they're asymptotically optimal, which is pretty amazing because I started with knowing everything, per instance labels, and now I know basically nothing. So just either fractions or nothing. and yet they're optimal. But of course, there are problems if you're not in the asymptotic regime. So here's just a little example, one-dimensional classification problem where I have two mixed samples and the fractions are set to be one minus the other one. So at 0 and 1, I have pure samples. And this is basically the AUC, how good the classifier is. 1 is, in this, units are very good, and 0.5 is very bad. And the point is that the black is the fully supervised case, and red and blue are these weak supervised cases. And they approach the black, so that's to say that they're asymptotically optimal. But when you get to 0.5, that's to say the two mixed samples are identical statistically. So obviously, you can't learn in that case. And so you see they tank. And basically, there they learn nothing. And the steepness of this peak here changes as you have more data. As you add more data, it becomes steeper and approaches a delta function. So that's great. I just want to very quickly say that techniques like this can even be used beyond classification. And so we've thought about it in the context of anomaly detection. So suppose there's some new physics you want to uncover from the data without knowing anything. Well, you have to know a little something. So let's suppose you have some, for instance, time series data, where there's some one dimension where the spectra of the not new physics is smooth. So in this case, there's some distribution where everything is smooth if it's just the background. And you happen to know ahead of time that if there is something new, it's peaked. And that's all you know. Then you can play the same game. You can make a mixed sample of new stuff and old stuff. And then you can have sidebands, which are mostly old stuff. And then you can use all the other dimensions that you have in your data to train a classifier to distinguish the signal region from the sideband region. And then you can, once again, find something new without knowing basically anything about the structure. Other than that, there's one dimension somewhere in the data that's special where it's resonant. OK. And yeah, maybe if this method works, you can get a flight to Stockholm, which would be great. One of the reasons I'm particularly interested in these techniques is that so far, the Large Hadron Collider, which is probing the smallest distance scales with a terrestrial laboratory, has found no new signs for new physics. But it could be that we're looking in the wrong place. And this might help find something without a theory bias. All right, so that brings me to regression. I promise I'll spend less time on regression and generation. I wanted to go through the classification example in more detail. So the one thing I want to talk about with regression is calibration. And the example I'm going to have in mind is energy calibration. So this is one of the things that I spent a lot of time thinking about, and any experimentalist will spend a lot of time thinking about calibrating your detector. So this is a plot that shows basically the expected value of the reconstructed energy over the true energy. And you'd like this to be 1. That would mean that your detector is calibrated. And this is basically different parts of the detector. And you see it has this really crazy trend. And that's just because there are different detector elements, different technologies, and so it looks really crazy. And you'd like to calibrate this to make it 1. This calibration, this response here might depend on not just where you are in the detector, but many other features. And so in principle, there's some features theta where you'd like to make this calibrated as a function of. OK, so what you'd like to do is you're sitting there thinking how I would calibrate. Let's say you have some simulation, and you have some detector energy and some true energy. Maybe what you're going to do is do regression with mean squared error. That's like the first thing everyone would try. So you minimize this function to get the g, which is the optimal calibration function. When you do that, you probably know from taking the statistics class that what the function is going to learn, what is f? F is nothing other than the expected value of y given x. If I'd use a different loss function, maybe if I had used the mean absolute error, it would be the median instead of the mean. But the same story still holds. It's this. And I'm going to claim that's a bad thing. And we don't want to do this, even though this is probably the thing that most people do. And the reason is because if you ask, what is the expected value of the calibrated energy in bins of the true energy? So the expected value of the calibrated thing given the true thing. And you don't have to go through the math, but basically the punchline is that it's not y. So this value is not equal to y, even if your training spectrum is not the same as your testing spectrum. So basically, given the true, the average calibrated is not true, which is bad. And so you build a dependence on the prior, so that's bad. Even if you had the right prior, it wouldn't close exactly. So this is bad. And it turns out there's many solutions to this problem. One very simple solution, which is kind of elegant, which is just to do the other thing around. So instead of learning true given measured, do predict measured given true, and then invert that function numerically. And so we give this a stupid name called numerical inversion. And basically, if you do this procedure, it by construction is independent of the prior. under some certain assumptions, it closes. So that is the expected value of the calibrated energy, for instance, is the true energy, which is great. That's what we want. And you can do this also with neural networks, and it can also work with many features. And so let's say that there's not just x and y, but I also have some thetas. So I have many additional features that my calibration depends on. And in that case, suppose I also want to correct for the dependence. And so here's a plot that's very complicated, but I try to explain it in 30 seconds. So this is, once again, there's some channels that I want to have my response calibrated as a function of. So this is the residual calibration, so the expected value of the measured given true as a function of some feature. And I like this to be flat, so not just calibrated, but also independent of this parameter, this number of channels. And basically the point is that you can do this not just with a single inversion, but you can do simultaneous inversions, and therefore control for all the features you like. So this simultaneous approach is using neural networks basically to make my calibrated function it's not only calibrated inclusively, but also as a function of all my thetas, which is great. And this can be done basically by using a simple mean squared error, but the clever trick of reversing your target and your input. OK, so now on this whirlwind tour of reducing simulation dependence, I have one more example from generation. And the idea is going to be, we've heard a lot about GANs and other generative models today to, for instance, accelerate simulation. And I've spent a lot of time thinking about accelerating simulation. But today I want to talk about augmenting simulation or replacing it. And the idea is, can I use information about physics plus generative models to learn information about the data? And so one example is that there are many cases where we know that the distribution of, let's say, a radiation inside an event factorizes. So given some information, I know that I can model the generative process, and it's independent of the rest of the event. So imagine I could take a region of interest inside in my event, train a generative model, and then attach that generative model to other parts of the event. And so that's what's shown here. We have a GAN where we have some particles, and we know that the distribution, say, there are many kinematic features of these particles, so say their energy, where they are, and some other things, and this is the mass. And I know that the mass basically is independent of other things in the event, given all these other features. So I can strip off the mass, learn a GAN, and then I can use that to basically attach my GAN to other parts of the irradiation in the event, and this allows me to make a prediction based totally on data, where the training is done totally on data. And the last plot I'm going to show is basically to say that the old approach has a very large uncertainty because it depends a lot on simulation, whereas this new approach learns directly from data and can use GANs in a sort of nice and straightforward way. OK, so I've given just a few examples of how we can reduce simulation dependence. And I think that I haven't really focused too much on any particular deep neural network architectures. But the point is that these are sort of generally useful. And I've applied them to particle physics, but I think they have broad applications. And I think that they help us learn something new and exciting directly about nature. Thanks.